We move on to another important topic, which is the ideal gas and the ideal gas law. By ideal gas, we mean a gas that its atoms, its molecules are considered free. So there is collisions between the atoms and the molecules, but these collisions are random and does not make much of a difference. When we describe gases, we usually deal with Avogadro's number. This number, 6.02 by 10 to the power 23. This is the number of particles, atoms, or molecules per mole. Per mole. And the number of moles, if you have any number of atoms or molecules, the number of moles can be calculated from this simple formula. Take the mass, divide the mass by the molar mass, you get N, the number of moles. We see here in the periodic table all kinds of elements, including gases. So when we describe elements, most of the time we need the molar weight for the substance, and usually we take carbon as a reference. Carbon 12 has a molar mass of 12 grams. Okay, so 1 mole of carbon weighs 12 grams. In plain English, if you bring 6.02 by 10 to the power 23 atoms of carbon and them, the mass there will be 12 grams. This is what we mean when we say the molar weight for carbon is 12. Okay? So you bring this number, multiply it by 12. U is the atomic mass unit. We consider the mass of carbon 12 atomic mass unit. So each atomic mass unit is 1 part out of 12 parts for the carbon 12 atom. And here we are using the conversion factor that 1 atomic mass units correspond to 1.6 by 10 to the minus 20 gram. When you simplify this equation, you get M equals 12 gram. This is the mass of 1 mole of carbon. In general, you take the molar mass divided by Avogadro's number to get the mass of a single atom. Okay, so for helium, for example, the molar mass is 4 grams. Divide that by Avogadro's number, you get 6.64 by 10 to the minus 24 gram per atom. This is the mass of 1 helium atom. Usually in the periodic table, you will read this information. The numbers here, unfortunately, the font is not big enough, but the numbers here will give you some information about the molar mass for various elements in the periodic table. We move on to the behavior of the ideal gas, and in this regard, we have 3 important laws. The first law is Boyle's law, which is simply common sense. If you increase the pressure, think of this cylinder and this piston, and you have ideal gas here. If you increase the pressure, the volume will decrease. You have inverse proportionality between pressure and volume. Right? The greater the pressure, the smaller will be the volume. This is called Boyle's law. Then the relationship between temperature and volume, it is direct proportionality. If you increase the temperature, the volume will expand. That makes sense also. That's called Charles' law. And the third law is between pressure and temperature. Again, it is direct proportionality. If you heat the gas, the pressure gets more, or if you increase the pressure, the temperature gets more. This is the Gay-Lussac's law. We put these three laws together and arrive at this law, which is called the ideal gas law, which says PV, the product of PV equals nRT. N is the number of moles, R is a universal gas constant, it is equal to 8.31 joule per mole Kelvin. Okay, so in this equation you have PV and you have T. Usually we will need these three parameters, the pressure, the volume, and the temperature. When we want to study the gas, when we want to describe the gas, we will need these three parameters: the pressure of the gas, the volume of the gas, and the temperature of the gas. So with this equation, this is very important equation. If the gas change the condition, so now you have a new value for P, a new value for V, a new value for T. So you can write this equation: P1 V1 equals nRT1, then P2 V2 equals nRT2. You divide the two equations, you end up with a new equation: P1 V1 over T1 equals P2 over T2. This equation, this form of the ideal gas law, allows us to solve problems. It is a very powerful law. Okay. Now, as we speak about gases, another piece of information that is relevant: 1 mole of ideal gas at atmospheric pressure, okay, and at 0 Celsius will occupy a volume of 22.4 liter, regardless of the gas, whether it is oxygen, whether it is hydrogen, whether it is argon, you name it. All gases will have this volume per mole at atmospheric pressure and at 0 Celsius. Here, some useful equations. If you want the number of moles, say you have n number of atoms. To get the number of moles, you divide that number by Avogadro's number. As simple as that. Okay, so here the number of moles n, you get it dividing the number of atoms by Avogadro's number. Okay, so we arrive at this equation here, and the ratio between R and Avogadro's number is a constant and R is a constant. This ratio is a third constant, Kb, Boltzmann constant. So the ideal gas law is written sometimes in this form: PV equals nRT using the number of moles, and sometimes it is written in this form: PV equals nkBT, and N now is the number of atoms rather than the number of moles. Okay, so depending on the problem, sometimes we use this form of the ideal gas law, sometimes we use this form. So Kb, Boltzmann constant, is equal to the ratio between R and Na, which is 138 by 10 to the minus 23 joule per Kelvin.